this is lesson 14, and this has to do with a transformer. Transformers are quite useful in lots of places, so I wanted to do this to show you sort of how a transformer, how and why a transformer works. So what we have here, I have a DC, remember this is the figure for direct current power supply or battery that we used in Unit 1. And then I have this coil, so this wire is wrapped around this iron core, and the core is here, this piece of iron is here to direct magnetic field lines and kind of keep them going in the same direction. Now there's some of this that goes back to the general physics and magnetic fields and how they're created or what they're the result of. I will explain a little bit of that as we go, but the major part of this is to understand a couple of equations toward the end to see how you get various voltages when you have only a certain voltage available. So the details of how it all works you don't really have to remember, although I will explain it as we go. Well, if you perhaps remember or don't remember, the equation for the magnetic field is B, is mu 0 I over 2R. Mu 0 is a constant, I is current, which we've used before. Now this R is the radius of the circle. So this is the magnetic field at the center of a loop. Okay? So the magnetic field, if we have current in this loop, and if there's more than one, then we would multiply by N. We don't really need to worry about that at the moment. The important thing is that there's a magnetic field at the center of this coil, and it is due to the current and also to the size of the coil. Now, in the LR circuit, we did a little bit about using coils, but I'm also going to describe more here. So the other thing that we need to look at is flux. So we have magnetic flux. It's represented by the capital Greek letter phi. If you remember, the phase angle in the phasor diagram was phi, but it didn't have these little bars across it, so it was a lowercase Greek letter. But this is flux, and flux is defined as the number of loops times the magnetic field times an area times cosine of an angle. Now, the way we look at this is if we have a side view, this is a side view of a loop of wire. So if you had a loop of wire and you were looking at it from the side, this is all you would see. Now, the crucial thing is that the direction of the area of the surface of the loop is perpendicular to that surface. That's the one thing that students always don't remember, and then they get everything confused. So we're going to call this A, and I'm going to put a vector sign over it. Then the magnetic field can be oriented any direction. I'm going to actually draw it at an angle and put B there, B vector, and then this angle is the angle theta. So the angle theta is between the direction of the area and the direction of the magnetic field. Now, we don't really need to remember too much of this, but there are parts of it that we do. Now, let me find a wire here. Basically, what we want to think about is if we have a loop. So now if you have the loop, if you're looking at it from a side view, then pretty much a straight horizontal line is all you see. Now, the other thing to do is think of this as the top of a bucket or, I don't know, a Walmart bag that we have inside of here. And if you're outside in the rain and you want to catch water, you hold it like this, assuming the rain's coming fairly straight down. If you tilt this way, then you're not going to catch any rain. So the rain is analogous to flux. So you want to know how much of this magnetic field is actually getting through the area. So that's kind of what all of this is about. Now, we're going to answer some questions. Notice that this is direct current, so we're going to look at direct current and then we're going to look at alternating current and see what the difference is and see how all that fits. Okay, so on the top of the next page, number 3, says, is there flux through coil 2? Well, there was supposed to have been another question over here. Step 1 says to draw an arrow to indicate the direction of the magnetic field through the center of coil 1. Okay, so I have to make sure I read my instructions there. So we have the wire. Notice that this is the positive side of the battery, so the current comes out the positive side, goes that direction. So the current is going around this direction. It's like behind here and in front and back behind. So if I make my fingers do the same thing that this current is doing, my fingers will go like this. My thumb points down, so the direction of the magnetic field is from top to bottom here. Okay? Well, the purpose of this iron core is to direct the magnetic field. So it keeps this magnetic field here confined, and it goes here and it goes over. So the magnetic field will go up on this side. Now, it's not due to anything over here. It's due to this left side. But the point is, the magnetic field goes around, stays within the iron core, so it kind of follows around like that. Okay? So our question, is there a flux through this coil over here? The answer is yes, because there is a magnetic field. But the important thing is the flux changing? Well, if this is going around here, this is a constant value. There's no reason for it to change. So this field is a constant, this field is a constant, and so the flux is a constant. So the important thing is it's not changing. Now, number 4, will there be an induced voltage in coil 2? Well, we have to go to another term, another law in sort of the magnetic section, and that is Faraday's law. So we're learning lots of laws, mostly to make sure you can kind of see the progression of our thought processes, but in the end, we'll make sure that you know what you need to remember. Okay, so Faraday's law says that an induced voltage is minus the change in flux divided by the change in time. Now, you should sort of be familiar with this concept from a couple of the other lessons that deal with inductors, because that's basically what this is. It's a coil, and that's what an inductor is. And in the other lessons, we found that a changing current and a changing flux produced an induced voltage. So here, if the flux is changing, then there will be an induced voltage. So it's not only the fact that it's changing, but it's the rate at which it's changing. So if it changes very slowly, not really much effect is happening. If it changes rapidly, then there's a large effect. But at this point, there's no changing flux because there's nothing changing anywhere. So there is no induced voltage. If there's no induced voltage, there's no induced current. So the point of this is that with a direct current, you don't get any result over here. It doesn't hurt a transformer. It's just that when you first close the switch, there will be a little momentary response and then nothing else happens. So there's no point in connecting a transformer to a direct current. So now we're going to look at an alternating current. Okay, so I have these equations here. We really don't, I'm going to erase these. I don't think we really need these. Don't need this. And if you've written this down, then you can refer back to that if I talk about that. So what I'm going to do here, instead of redrawing the whole thing, I'm just going to redraw and make it to the picture in part 2. So I'm going to erase that, and I'm actually going to erase these magnetic fields here, and then put my picture back together. So over here, I'm going to have an alternating voltage source. So we have those wires put back together and these wires put back together. Okay? So now we have current, and I'm actually going to put an arrow up here. It's in the picture, both directions. So it tells you that the current goes one way, then the other way. This goes back to basically what we started with in lesson 8. Voltage is the maximum times the sine of omega t. So we have an oscillating or an alternating voltage there, voltage source. So the question is there flux through coil 2? Well, oh, yes, kind of forgetting where I was at here. So when we have current in this, there is a flux and there is a magnetic field. Well, actually there's the magnetic field first and then there's a flux. The magnetic field, remember, continues around and up through here. So whatever the flux is here will be the same as over here. Now, so then we go on to the other questions. Will there be an induced voltage in coil 2? And the reason is yes, because this magnetic field that's here and the flux that's the result of the magnetic field, that flux is changing, so if it's changing, there will be an induced voltage. And then the next part is, will there be an induced current? And the answer is yes, because if there's an induced voltage, there will be an induced current to go with it. And then the last part is, will that current be direct or alternating? And it will be alternating because basically everything's changing all the time. So there will be no direct current or direct anything. It will be alternating. So that explains why, or sort of the basis of operation for a transformer. You have an alternating voltage source over here. There's a magnetic field. The magnetic field is changing, so the flux is changing. That field goes around through, stays in the core. The field is changing here, so the flux is changing. If there's a changing flux, then there will be an induced voltage, and as a result of that, an induced current. So you will end up with a current over here on this side, and that is not connected to a voltage source. So that's kind of the whole point, is you have a voltage source one place and you end up with a current in another place. Now, we want to look at how all of these things are related. So we're going to look at primary and call number 1 primary because it's with the source. You might want to make sure that you don't get S for source and S for secondary mixed up. So I don't think I use source in here at all. We're just talking about the primary and the secondary. So the primary goes with the original and the secondary is what we're trying to produce over here. So on the next page under primary and secondary coils, it describes those. I'm going to go through these derivations. I think you probably could, but this will save you a little bit of time. So what we want to do is for the secondary, the induced voltage is minus. Now the minus has to do with Lenz's law and the fact that the coils react so as to oppose the change that caused them. If you want to look this up, it's Lenz, and that will explain a little bit more about why these things and how these things behave. It's going to turn out, it doesn't really matter whether we have a minus there or not because it'll cancel a little bit later. So for the secondary, we're going to have the change in flux, and I'm going to call it a subscript B for magnetic field, and then I'm going to put a capital T for total. So this expression is going to account for all of the wires, all of the loops. And then that's divided by delta T. Now, what we're going to end up with in these two sides of the transformer, we're going to have different numbers of loops. So we need to get into the equation explicitly. So I'm going to put minus capital N, and it needs a subscript S for secondary, and then we're going to have this as the change in the flux, the magnetic flux, for one loop. So basically our total is going to be the number of loops times the flux, the change in flux for one of those, and then we need to still have divided by delta T. The next step, we're going to write the same thing for the primary. So we have minus delta phi of the magnetic field total, and this is over delta T, and probably, I don't know, we could have put primary in there if we wanted to, but we don't really need to. Okay, so now then, we have the number of turns in the primary and the change in flux for one loop, and then divided by delta T. Now, in doing this, we sort of were assuming that both sides of the transformer are the same size, so that this change in flux for one loop on the primary side is, or the secondary side, is the same as the change in flux for one loop on the primary side. And if you actually look at any transformers, they really are about, they're the same size on both sides. I don't think you will find them that have a big side here and a little side there. They generally are the same on both sides. Now, I guess if you had one that really was different, then you would have to go through and derive some other equations. Okay, so what we're going to do now is to assume that this change in flux for one loop per time, that this rate here is the same on both sides of the transformer. So if those two things are equal, then we could solve for each of them and set that expression equal to each other. So I'm going to kind of do a couple of steps and show you the result. But if you want to write out a few more steps, that would be fine. So you would solve for this and solve for this, and then set those two equal to each other. So if you solve for this, you're going to get minus Vs over Ns, so I'm going to put that here, minus Vs over Ns. And then if you solve for this, you're going to get minus Vp over Np. So equals minus Vp over Np, and of course both minuses we can change to pluses. Now, that is a significant equation. This is definitely one that you want to keep track of. And it goes in the box there, says voltage equation for a transformer. So if we have a voltage on the primary side, and I'm going to erase these pluses because I'm not used to them there. So if we have a voltage on the primary side, and we know how many turns there are on each side of the transformer, we can figure out what voltage we'll get out on the other side. Now, a different approach, of course, which is probably what's done, you don't just make all these random transformers and then try them out and see which one gives you the voltage that you're looking for. So if you have a voltage and you know what you need out on the other side, then you can decide on the number of turns in both of these places to get that proper voltage. Now, what you might think is, why don't I just have one or the other of these as one, like one turn, and then the other one be several turns? Well, there are other considerations in constructing a transformer that will tell you that you need more than one turn on a side, and we're not going to get into that. So if you know how many turns are on one side and you know maybe how many are on the other side, that'll tell you another voltage, or you might know what the primary voltage is and what you need for a secondary, and you may know one or the other of these ends, and then you can calculate the other one. Basically, there are 4 quantities in that equation. You have one equation, so you can solve for one of the unknowns, but you have to have the other 3. Okay, now there are a couple of other considerations. This tells you something about voltage and the number of turns. And if you look at this kind of closely, if you have the primary, and if you put a lot more turns on the secondary, you're going to get a higher voltage out on the secondary. So your first thought, it might be, oh, well, that's good. I can put in a little voltage and get out a big voltage. So I'm sort of getting something for nothing. Well, it's really not like that, and that's pretty much the case in everything. You don't get something for nothing. You may get something, but it's at the expense of something else. So the other thing we have to consider is power, and we've talked about power before in the first unit. We know that power is related to conservation of energy, so that's kind of a big deal in this. So we know that power is current times voltage. So we could say that the power for the secondary must be equal to the power for the primary. This is based on conservation of energy, and I'm not going to spell it all the way out. Conservation of energy. So you can't get out any more energy than you put in. Well, if we look at this, power is current times voltage, so we have current for the secondary times voltage of the secondary is current times the primary times voltage of the primary. Now, if we go back to this was in terms of ratios. So if we had more turns in the secondary, we got more voltage in the secondary. But if we look over here, current times voltage is a number. So on the primary side, this number is whatever it is. Now, if we happen to get a larger secondary voltage by using the proper number of turns, we get a larger secondary voltage, what happens to the secondary current? Well, the right-hand side is a particular number for a particular case. So if the left-hand side, if one term gets bigger and the product has to stay the same, then the other term must get smaller. So what you're going to end up with here is you might get a larger voltage, but the result is a smaller current. So it depends on the exact situation as to what exactly you want there, or what you need to do. So this is what I call the current equation for a transformer, and this is in terms of the voltages. So this is another equation that you will need to keep track of. Okay? Then the last equation is to sort of combine these two. And you might want to know something about current, but you might want it in terms of the number of turns instead of the voltages. So we're going to put those together to get an equation so that you wouldn't have to use both of these to solve for whatever if you wanted to. Okay, I'm going to move this one over here. So IS VS equals IP VP. And then I'm going to erase this and we'll figure out our last equation, and then that's going to be all I'm going to talk about. And the rest of it has to do with step up and step down transformers, and it explains what those are and asks you some questions which you should be able to figure out pretty easily. So if I want an equation in terms of current and the number of turns, I can do a couple of different things. So what I decided was I'm going to solve for IP and say that that is IS times VS over VP. So I've just used this bottom equation here and solved for IP. And there's probably several ways you can do this, but I just decided to do this way. Well, now VS over VP, so I'll keep this. We can look at our top equation and we can rearrange the letters there if we do it carefully. I want VS over VP, and if you remember when you have a ratio and you want to move things across the equal sign, they have to move diagonally from numerator to denominator. So, or you could just multiply, cross multiply and resolve, however you want to do it. But we would end up with VS over VP, so that comes down here, and then NS would go up there. So if I have VS over VP, that's going to be NS over NP. And that is indeed what I have here. So there's several ways we could leave this, but I decided to multiply so that we end up with an equation that looks similar to that. So here we have IP NP is equal to IS NS. So we have our third equation. This is the equation that involves the current and the number of turns. So we've got three things, and we've got three equations. We have number of turns, voltage, and current. And each of our equations involves two of those. So actually, I think if you do some statistics, probability or something, you can figure out that once we have three equations, that relates everything that we need to relate. So we've got voltage and number of turns, voltage and current, and then current and the number of turns. Okay, so we're not doing an experiment with this. I'm not sure, I've not really seen any real good experiments for this. I suppose we could have measured some voltages or whatever. But I decided this is the end of the unit on alternating current, so it's probably time for you to be catching up and getting everything done. As I said, there's a few more questions in the rest of this about step up and step down transformers, and then of course there's some homework. So this is the end of Unit 2.